Welcome everyone. Everyone to Dr. Carminati's YouTube channel. I'm thrilled to see you here today as we dive into an exciting, mind-bending topic. Quantum computing hype versus reality and real-world applications. Whether you're a tech enthusiast, a curious learner, or just stumbled across this video, you've landed in the perfect spot. Today, we'll unravel what quantum computing really is, cut through the hype to reveal the reality, and explore real-world applications, both those emerging now and those still on the horizon. I'd love for you to stick around, share your thoughts in the comments, suggest topics for future videos, hit that like button if you enjoy this journey, and subscribe to join our growing community of explorers. Let's jump right in. First, let's tackle the basics. Quantum computing represents a groundbreaking shift in how we process information. Unlike the classical computers you use every day, like your laptop or smartphone, quantum computers tap into the strange, fascinating world of quantum mechanics. This field of physics governs how particles behave at the tiniest scales, such as atoms and electrons. Classical computers rely on bits as their building blocks. A bit acts like a simple switch. It's either a 0 off or a 1 on. Picture a row of light switches, each one clearly set to one position. Quantum computers, however, use quantum bits, or qubits. Qubits behave differently because of a property called superposition. This property called superposition means that a qubit can be a 0, a 1, or both at the same time until you measure it. Imagine a coin spinning in the air. It's not just heads or tails, but a blend of both until it lands. This ability lets quantum computers explore many possibilities simultaneously, unlike classical computers, which handle one option at a time. Then there's entanglement, another quantum superpower. When qubits entangle, they link up so that changing is one that instantly affects the other, no matter how far apart they sit. Think of two dancers perfectly synchronized across a stage. One moves, and the other mirrors it instantly. This connection allows quantum computers to perform complex tasks with incredible efficiency. So why does this matter? These properties, superposition and entanglement, enable quantum computers to tackle problems that would take classical computers millions of years to solve. But before we get too excited, let's dig into the hype versus the reality. You've likely heard big promises about quantum computing. It'll revolutionize industries, crack unbreakable codes, and solve unsolvable problems. The excitement buzzes everywhere, from tech blogs to sci-fi movies. But how much of this holds up today? The potential absolutely exists. Quantum computers could one day transform fields like cryptography, optimization, and scientific research. Yet the reality lags behind the headlines. Building a quantum computer proves incredibly tough. Qubits demand precise conditions. Think temperatures near absolute zero, colder than outer space, to function. Even then, they're fragile. Tiny disturbances, like a stray electromagnetic wave or a cosmic ray, can disrupt them. This disruption, called decoherence, causes qubits to lose their quantum magic, and the computation collapses. Scaling up adds another challenge. Companies like IBM and Google boast quantum processors with dozens or hundreds of qubits, but many groundbreaking applications require millions or even billions. Right now, errors pile up as qubit counts rise, making large-scale, reliable quantum computers a distant goal. It reminds me of the 1940s, when early classical computers filled entire rooms, yet barely matched a modern calculator's power. Quantum computing sits in a similar infancy, promising but not fully grown. The hype fuels investment and research, which drives progress. Still, we need patience. Quantum computing won't replace your laptop anytime soon. However, as a technology, it's carving a fascinating path toward a future that we are only beginning to imagine. So, what can quantum computing do today? Are there any commercial applications out there? Let's explore what's happening in the real world. Fully commercialized quantum solutions remain rare. Most applications linger in the experimental or pilot stages. However, big players and startups alike push the technology forward, offering glimpses of its potential. Take IBM, for instance. Through the IBM Quantum Experience, they provide cloud access to their quantum computers. Researchers, developers, and even hobbyists can log in, run small quantum programs, and test ideas. It's not powering businesses yet, but it opens the door for exploration. Google's Quantum AI Lab also makes waves. They grabbed attention with their quantum supremacy claim, solving a niche problem faster than any supercomputer could. While impressive, that feat targeted a specific test, not a practical, everyday use. Startups like IonQ and Rigetti Computing join the race too. IonQ builds quantum computers using trapped ions, think atoms held in place by electromagnetic fields, and offers access via cloud platforms like Amazon Braket and Microsoft Azure Quantum. Businesses can experiment without owning hardware. Rigetti follows a similar path, focusing on superconducting qubits. These efforts aim to make quantum computing practical, but they're still stepping stones, not finished bridges. What about specific uses? Optimization problems shine as a promising area. Volkswagen, for example, teamed up with quantum researchers to improve traffic flow in cities. By crunching data on a quantum system, they aim to cut congestion, a real-world win if it scales. Drug discovery offers another frontier. Quantum computers could simulate molecules with precision, speeding up the design of new medicines. Companies like Pfizer and Roche invest here, betting on future breakthroughs. Still, these examples stay experimental. No one's selling quantum-powered traffic apps or drugs off the shelf yet. The tech teeters on the edge of practicality, not fully across the line. Now, let's tackle a big question. Are quantum computers running AI applications like machine learning, ML, deep learning, DL, or large language models, LLMs? The idea sounds thrilling. Quantum speed boosting AI power, but where do we stand? Quantum machine learning, QML, has emerged as a hot research field. Scientists aim to merge quantum computing strengths with AI's algorithms. The goal? Speed up tasks like training models or crunching massive datasets. Google's Quantum AI Lab experiments with this, using quantum processors for tasks like classifying data or clustering patterns more efficiently than classical systems in some instances. IBM dives into developing quantum algorithms for feature mapping and optimization, key pieces of machine learning puzzles. But here's the catch. Today's quantum hardware lacks the muscle to outpace classical computers for most AI jobs. Training a deep learning model or running a large language model like the ones powering chatbots demands massive power and stability beyond what current quantum systems offer. The research looks promising in any case. Quantum computers excel at parallel processing, which could one day slash the time needed to handle big datasets or complex neural networks. For now, practical quantum AI applications stay in the lab. No commercial quantum computer runs a full-fledged ML, DL, or LLM system yet. The potential simmers, but it's not boiling over into the marketplace. Even if fully commercial quantum products remain scarce, some companies dip their toes into quantum waters with real projects. Let's spotlight a few. JP Morgan Chase partners with IBM to explore quantum computing for finance. They test algorithms to optimize portfolios, model risks, and spot fraud faster. Success could reshape banking, but they're still in the proof of concept phase. Airbus takes a different angle, using quantum systems to refine aircraft design. By simulating countless configurations, they hunt for lighter, cheaper, more efficient planes. Another pilot project with enormous potential. In energy, ExxonMobil collaborates with IBM to optimize power grids and distribution. Quantum computing could fine-tune how energy flows, cutting waste and costs. These examples, finance, aerospace, energy, show industries betting on quantum payoffs, even if the tech hasn't hit prime time. So, where does quantum computing stand? It's a thrilling, transformative field, but the hype outpaces the reality, for now. Challenges like error rates, scalability, and decoherence keep it in an early stage, much like classical computing decades ago. Yet the strides impress. From cloud-based quantum access to experiments in optimization, drug design, and AI, we see sparks of what's possible. I hope this deep dive clarified quantum computing's current state and its real-world promise. If you enjoyed it, please like the video, share your thoughts or questions in the comments, and subscribe for more explorations into cutting-edge topics. Suggest new video ideas too. I'd love to hear what sparks your curiosity next. Thanks for watching, and I'll see you in the next one.